In this video, we're talking about composite functions and their domains. And the most important thing to remember about the domain of a composite function is that in order to find the domain, you have to take into account the composite, and you also have to take into account what we'll call the inside function. So we'll come back to that in a second. In this particular problem, we've been asked to find the composites f circle g, g circle f circle f, and g circle g, given that f of x is x plus 1 over x, and g of x is x plus 1 divided by quantity x plus 2. So we've got these two functions. We need to find each of these four composite functions here, and once we find the composites, then we'll want to look at their domains. So let's start with the first composite here, f circle g. Remember that f circle g is the same as f of g of x. So in order to find f of g of x, we take g of x and we plug it in to f of x. So let's think about it this way. Here we're taking f of x. In other words, we're sort of plugging x into the function f. So we have x here on the right-hand side and x here on the right-hand side. If we want to plug g of x into f of x, then we need to replace every x value here with the g of x function. So on the left-hand side, instead of calling that f of x, we'll call it f of g of x. We replace this x here with g of x. That's going to be equal to, over here on the right-hand side, for both of these x values here, we'll plug in g of x instead, which is x plus 1 over x plus 2. So instead of x right here, we'll instead plug in x plus 1 over x plus 2. And then instead of plus 1 divided by x, we'll say plus 1 divided by our g of x function, x plus 1 over x plus 2. So x plus 1 over x plus 2. Now if we wanted to simplify this function, remember we've got here 1 divided by a fraction. Well, when we're dividing by a fraction, instead of dividing by the fraction, we can multiply by its reciprocal. It's the same thing. So instead of 1 divided by x plus 1 over x plus 2, we could instead change this to 1 multiplied by x plus 2 over x plus 1, the reverse of this, the reciprocal of this. So 1 multiplied by x plus 2 over x plus 1 is of course just going to give us the fraction result of x plus 2 over x plus 1. So now we've simplified this function, f of g of x, which is the composite f circle g, and we need to figure out its domain. Well, remember that for a fractional function like this, a rational function, it's only going to be undefined when the denominator is equal to 0. So if x plus 2 equals 0, the function will be undefined, or if x plus 1 equals 0, the function will be undefined. So in other words, if x is negative 2, then we get negative 2 plus 2 is 0, so negative 2 can't be in the domain. And here, if x is negative 1, we get negative 1 plus 1 is 0. 0 in the denominator, we can't have that, so x equals negative 1 cannot be in the domain. So for the domain, we'll go ahead and say, for the domain is all x not equal to negative 2 or negative 1. So that takes into account the composite. That domain takes into account the composite function. But whenever we're dealing with the domain of a composite, not only do we have to account for the composite itself, but we have to account for the inside function. So in this case, we have f of g of x. G of x is that inside function. So we have to look at the domain of g of x. Well, if we go back to g of x here, the domain for g of x is going to be all x not equal to negative 2, because negative 2 is the value that makes the denominator here 0, which we can't have. So the domain for g of x is all x not equal to negative 2. Well, in this particular case, we've already accounted for negative 2 in the domain, so we don't have to add anything else. We can just say the domain is x not equal to negative 2 or negative 1. So let's take the second composite then, g circle f. That's going to be equal to g of f of x, and if we want to find that, we have to take f of x and plug it into g. So over here for g of x, we have x. It's like we're taking x and plugging it into the function g. We've got x right here, and we've got x right here. So what we want to do is replace all of those x's with the function f of x. So here on the left-hand side, we've already replaced this x with f of x right here. Now on the right-hand side, we need to replace both of these x's with the entire f of x function, x plus 1 over x. So instead of x right here, we're going to say x plus 1 over x, and then we have our plus 1. That's our numerator. Then if we look at the denominator here, we have x plus 2. Instead of this x right here, we're going to replace it with the entire f of x function, so x plus 1 over x, and then we have our plus 2. Now we want to simplify this function, which we'll do by finding a common denominator within the numerator and within the denominator. So in the numerator here we have x plus 1 over x plus 1. So we're going to take the denominator here from this fraction, which is x, and we want to make a common denominator with the x term here and the 1. So in order to get the denominator of both of these terms to be x, we're going to have to multiply by x over x. So we're going to multiply this term by x over x, and we're going to multiply this term by x over x, so that the denominator will be x throughout. So here what we're going to get is x squared over x plus 1 over x plus x over x. That's the numerator. Then looking at the denominator here, same thing. We have this fraction 1 over x, so we want to multiply the other terms by x over x and x over x to get that common denominator. So then in our denominator, we're going to have x squared over x plus 1 over x plus 2x over x. Now we can combine these fractions because we have this common denominator. So here within the numerator, we're going to have x squared plus 1 plus x. We'll go ahead and reorder those terms. So we have x squared plus x plus 1. So we're going to have x squared plus x plus 1 all over the common denominator of x. That's just the numerator. Then looking at the denominator here, same thing, x squared plus 1 plus 2x. We'll reorder those terms to x squared plus 2x plus 1 dividing by x. Now we've got a fraction divided by a fraction. When we're dividing by a fraction, instead of doing that, we can multiply by its reciprocal, and that doesn't change anything. So we'll keep this numerator here, x squared plus x plus 1 divided by x. And then instead of dividing by this fraction in the denominator, we will multiply by its reciprocal. So we'll flip it upside down and say x over x squared plus 2x plus 1. So what that does is it gets us to cancel these x's here, and we're just going to end up with x squared plus x plus 1 divided by x squared plus 2x plus 1. So now we've got our composite function, and we just need to think about its domain. So the domain, of course, is going to be all x where the denominator is not equal to 0. So if we look at the denominator here, x squared plus 2x plus 1, we can factor that out to x plus 1 times x plus 1. So that's the denominator. The only way to get that equal to 0 is if x is equal to negative 1. So we know that the domain is all x not equal to negative 1, since negative 1 is the only value that can make that denominator equal to 0. So that takes into account the composite, but now remember we have to look at the inside function and its domain. So the inside function in this case is f of x. So we go back to f of x and we have to look at the domain of this function. Well, the domain of this function is going to be all x not equal to 0, because the only way to make this function undefined is if we put 0 here in the denominator, which would mean x equal to 0. So this domain is all x except x equal to 0. So we haven't already accounted for that in the domain of our composite, so we have to add it. And so we can say that the domain of the composite is x not equal to negative 1 or 0. So remember in that first example, f circle g, the composite f of g of x, we didn't have to add anything because the domain of the inside function g of x was negative 2, and we had already accounted for that with the composite. But for this composite f circle g, we only had x not equal to negative 1 after looking at the domain of the composite itself. We had to go back to the inside function f of x, see that its domain was x not equal to 0, and we had to add that because we always have to add the domain of this inside function. So let's quickly do two more examples here. We have f circle f, which is the composite f of x. In other words, we're plugging f of x into itself. So here we have f of x equal to x plus 1 over x. So we're just going to replace these two x's right here with this entire function. So instead of x right here, the entire function is x plus 1 over x. So we're going to put that in, x plus 1 over x. And then we have plus 1 over x. So plus 1 over, and then instead of this x right here, again, the entire function, x plus 1 over x. So again, we're going to need to simplify that. we want to find a common denominator within this denominator, which we'll do by multiplying this term by x over x. That's going to give us a denominator of x squared over x plus 1 over x. Of course, now we can combine those fractions and we can say x squared plus 1 all over x. So now we have 1 divided by this fraction here. Well, remember that's the same as 1 multiplied by this reciprocal, x over x squared plus 1. But of course, multiplying by 1 doesn't change anything, so this entire fraction here just becomes x over x squared plus 1, and we can rewrite this whole fraction here as x over x squared plus 1. So we get x over x squared plus 1. Now we can say that the only way this function is undefined is if this denominator is equal to 0 or if this denominator is equal to 0. So this denominator will be equal to 0 if x is equal to 0. So we can say that the domain is all x not equal to 0. To get this denominator equal to 0, we actually won't be able to do it because if you think about it this way, any value we plug in for x, whether it's positive or negative, when we square it, it'll become a positive value. Even if we had 0 and we squared it, we'd get 0. And then we add 1 to it, we're always going to end up with a positive number. So there's no way to get this denominator equal to 0, so the domain of the composite is just all x not equal to 0. But then remember, we have to look at the inside function, f of x, and its domain. The domain of f of x is all x not equal to 0. We've already accounted for that, so we've got the domain of the composite. And finally then, moving on to the composite g circled g, that's going to be g of x, so we're plugging g of x into itself. So we've got g of x here. We need to replace both of these x's right here with the entire function. So instead of this x right here, we'll take the entire function. We'll say x plus 1 over x plus 2 plus 1 in the numerator. And then in the denominator, instead of this x right here, we'll put in the entire function. So x plus 1 over x plus 2. And then we have our plus 2. So if we want to simplify this here, we'll multiply this 1 by x plus 2 over x plus 2 to get a common denominator within the numerator. So we'll then end up with the fraction x plus 2 over x plus 2. In the denominator, same thing. We want to multiply this 2 by x plus 2 over x plus 2. When we do that, we'll have a denominator of x plus 2, but then we're multiplying the numerator by 2 because remember we had a 2 here. So 2 times x plus 2 is going to be 2x plus 4 when we distribute that 2 across the x plus 2. So now we have common denominators, and this numerator here becomes x plus 1 plus x plus 2 all over x plus 2. So we end up with 2x plus 3 over x plus 2. And then in the denominator here, we have a denominator of x plus 2, but the numerator is x plus 1 plus 2x plus 4, which is going to be 3x plus 5. Now instead of dividing by this fraction in the denominator, we can multiply by its reciprocal, and we get 2x plus 3 over x plus 2, multiplied by the reciprocal of the denominator, which is x plus 2 over 3x plus 5 when we flip it upside down. Then we can get this x plus 2 and x plus 2 to cancel, and what we're left with is just 2x plus 3 over 3x plus 5. And of course, the only way to get that domain to be undefined, the only way to get the function to be undefined, is when the denominator is equal to 0. So how do we get 3x plus 5 to be equal to 0? Well, we'd subtract 5 from both sides, and we'd get 3x is equal to negative 5, or x is equal to negative 5/3. So the domain is going to be all x not equal to negative 5/3. That accounts for the composite, but we haven't yet accounted for the inside function g of x. So its domain is all x not equal to negative 2, so we have to add that to our domain and say the domain of this composite is all x not equal to negative 5/3 and negative 2. And now we have the domain of the composite. So that's how you find composite functions and their domains.